Welcome to Gabversity, where facts don't give a flying fox about your feelings. Lovely to see everyone again. We are going to talk about some basic applications of calculus, and it is important to do that so that when we get back to quantum mechanics, you have some idea of what the hell we're talking about. So what I'm going to do is I'm going to imagine, hello, Nelly Bell, Michelle, G, everyone's here. All right, so let's get cracking. What we're going to do is I'm going to show you the application between for calculus and how it works, peripilo, how it works for speed, distance, and acceleration. I'm going to show you that through a person walking and a person driving. And then that will help you get why calculus is so amazing and how Newton, and I'm pretty sure, I can't remember who the other guy was, I think it was Hooke. It was Hooke? I always forget his name, who it is, the other guy who invented it at the same time. He actually invented it slightly before Newton. But anyway, let's get into this. So, what we're going to see, right? We're going to see that we have here Anthony Pearson is standing here at time equals 0. Now, after 1 minute, Anthony is here. Okay, after 2 minutes, he's here. Okay, so that gives you his distance over time. Okay, his distance is here after 1 minute or 1 second or 1 hour, whatever you want, one something, and his distance here is 2. So it looks like he's traveling at a constant speed. Now I'm going to convert this to a graph. How do we do that? Well, we have here his distance, right? And here we have time. So we saw at time 0 he's at distance 0. At time 1, okay, at time 1 his distance was 1, because it looks like it's pretty even. Okay, at time 2 his distance is 2. Now what you notice is that is his chart. Alright, now what importance is this? What the hell does this even mean? Well, what's interesting is that here we have an equation. We have that for each t that goes up, right, x goes up by 1. So when t goes up by 1, x goes up by 1. Well, what does that equal? That means that x equals t. X equals t, because when x is 2, t is 2. When x is 1, t is 1. So he's going up at a constant speed, but we can't tell that it's a constant speed yet. But how do we know? How do we know it's a constant speed? Well, because what we're going to do is we're going to get the derivative of this line. dx with respect to time equals 1. Right? That's it. Now, how did I get that? Well, all you have to do is this, right? This t, right? That is actually t to the power of 1. Here, it becomes, that 1 comes down here, and it becomes 1 times t, and that 1 goes down by 1, t to the power of 0. 1 times t to the power of 0 equals 1. So that shows you how powerful calculus is, that when you have the distance and over time, then you can calculate the speed. Now, what's his acceleration? Well, the acceleration, there's no t anywhere. So dx dt of the speed equals 0, which means there's no acceleration. So basically, he's traveling at a constant speed. Right? There's no acceleration at all. And if I wanted to go backwards, let's just say that, let me pick someone who has given us lots of hearts. Let's have a look. I used Nelly before, so this time I'm going to go with Michelle. So let's say that Michelle, sorry, I've got a lot of sun happening here. Let's say that Michelle, right, is accelerating at 1 units over time. So 1 x per second, because that's acceleration. 1, no, she's accelerating at 1. Well, let's now integrate it. The integral, right, from start to finish, so start is 0, finish is x, right, of 1 dx, right, is going to equal x 0 to x, which is the same as saying we put x in there and we put 0 in there, x minus 0, which equals x. All right, so now her speed is x units, let's just call it feet per second. Right, her speed is x feet per second. Right, which is interesting because that means that when time is 0, her speed is 0, but when time is 1, her speed is 1. When time is 2, her speed is 2. So if we chart her speed, now this is speed, so this will be feet per second, right? If we chart that versus time, it's going to be constant, because after 1 she's traveling 1, after 2 she's traveling 2. Now look at this, her speed is increasing as time goes by. She's getting faster and faster and faster and faster and faster. All right, so what does that tell you about her distance? Well, this is going to be interesting. What is the integral from start to finish, okay, of her speed? Well, her speed is x, so if we integrate that, that's actually x to the power of 1, right? We add 1 to that and we divide by this new power, so that's going to equal x, 1 plus 1 is 2, divided by the new power 2, right? From 0 to x, so we chuck in x, and then that's going to be, when we put 0, that's 0, so that's going to equal x squared over 2 feet. So that means that whatever time is, right, the distance is going to increase at this rate. So if time is 1, then her distance is going to be a half. If time is 2, her distance is going to be 2 squared is 4 over 2, which is 2. If time is 3, it's 9 over 2. All right, so her distance is getting pretty damn quick away. So if I was going to chart that, if I'm charting her distance, right, then her distance is actually sort of going to look like this, right? And that's distance, and that's time. So as time increases, her distance gets further and further away more quickly. Isn't that stalking? It is. It's mathematically stalking her. Absolutely. So look what happens. That turns into that, and then acceleration is constant. Acceleration was just 1. In other words, her acceleration is constant, which makes her velocity increase, or her speed increase, which makes her distance increase. This one here looks like it, doesn't it? It looks like what happens in people's pants. Oh, that's bad. That's actually terrible. I didn't even see that before. Now I can see it. All right. Now what's interesting is that the integral, which gives us this, right, is also the area under the curve here. So what turns out is that this area happens to equal this graph, if you add all the points on this graph. Someone's got something on their mind. What is the above graph? That is the speed. That is the distance over time. That's the distance over time. That's the speed over time. So the speed over time is increasing. Distance over time is increasing rapidly because the speed is increasing. So as time passes, you're getting faster and faster and faster. You see? So there you go. That is very, very interesting stuff. And that is the whole point of calculus. Calculus, right? This here is going to equal, right, this graph is x squared on 2. X squared over 2. Sorry, x squared over 2, right? Or x is t squared on 2, I should say. T squared over 2. All right, that means that the distance x is always related to the time squared on 2. So what is the point of this? The point is that there is a relationship between distance, speed, and acceleration. And you can calculate what it is mathematically. Hey, hello. So as we said, let's say that Michelle, we can now tell that if Michelle, right, if Michelle is accelerating in one direction at 1 foot per second, whatever, or meter or mile or kilometer, whatever you want, doesn't matter. If she's accelerating at 1 something per second, or minute per minute, whatever, right? Then we know her speed is going to increase, and it's going to increase at in a linear relationship to time, which means that as every second that passes, her speed's going to also go up by 1 unit. So after, let's say after 1 second, she's going 60 miles an hour. After 2 seconds, 61, then 62, then 63. Stupid phone died. Yeah. That happens. Alrighty. And now it's getting a bit warm, which is beautiful. I love it. Now it's warming up. We're cooking with gas, ladies and gentlemen. Alrighty. So we can use calculus. If we know your acceleration, we can use a calculus, which is the reverse derivative going up a chain. We can go up and get your speed. And then if we go up again, we can get your distance over time. And we'll know exactly where you're going to be at each location at whatever given point in time. And we can do the reverse. If we know all of your locations at any given point in time, we can derive that and get your speed at any location at any time. You are fast. And then if we derive it again, we can get your acceleration at any point in time. So that's the whole point of calculus. And I'll show you the graphs again, right? Here is the first graph, which is that's your distance over time, and it's going up at this fashion, which is like that, right? Your speed over time is going up at this. Your speed equals time, so your speed is just going up in a linear fashion. Your acceleration would be constant. It would always be the same. It's always 1. And if we want to go backwards, as I said, if we started with this and wanted to go here, well, we know that the speed is 1-to-1 ratio, right? And so we integrate that and we get x squared over 2, and that's how we get your distance versus every point in time. So that is the point that is an applied version of basic calculus, right? And I'm going to show you what the formula is, the very basic. There are many formulae, right? But I'm going to give you the very basic one. Looks like someone's going by ambulance somewhere. One of our neighbors. We'll see what happens. All right. So if you have a graph, I'll show you the pattern. If Michelle's distance over time is mapped by x squared over 2, right? Or let me call it t squared over 2. So that means that whatever the time is, chuck in the time in there, and you'll get the distance. Okay. Then if you want the speed, you have to derive this. So d dt of this, right, equals the speed. Okay, and it's actually velocity, but so this is not completely correct, but just to give you an idea. And that is going to equal t, because what we do is you take the 2, you bring it down, and you times it, so that 2 will cancel out with this 2, and then you take away 1 from here, and you're left with t1, which equals t1, which equals t. Now if I derive that again, d dt of t equals 1, right? That means that because what I did was I took t1 and I put it down here, so 1, and then I made that 1 minus 1, right, which equals 1 times t to the 0, which equals 1. So the acceleration is constant. And why is that important? Well, we've used your distance over time to find out what your acceleration is, all right? And that's the formula. Now we can actually skip the, like if we add that to that, if we derive the distance graph, we get speed. But we can skip speed and go straight to acceleration. How do we do that? We do this. We say d2 of t squared over 2 dt squared. Okay, so what we've done, this is now equals acceleration immediately. Alright, it's actually, yeah, so that here, okay, is the second derivative. Exactly. Hi, Van is back. Welcome back, my friend. Alrighty, that is the second derivative, which is called acceleration. So instead of getting the first derivative of this to get speed and then deriving the speed to get acceleration, you can skip by using this. Okay, and I've written it in a partial form because it's one dimension. Alrighty. And so now when you see in quantum mechanics all the second derivatives we're doing, you are seeing that we are skipping one step. That is the point of the second derivative, right? And you can have third, fourth, fifth, sixth, and it depends, of course, if the function is continuous, which means obviously that Michelle exists at every single point, which in our universe, at our size, that happens. At smaller scales, that doesn't happen. You know, just like traffic lights, like it can be green and then go orange, but it doesn't travel in between. That's quantum mechanics. That was my introduction to you guys on calculus. Once we get our Patreon subscribers to 2,000, I'll be able to do like a full-blown calculus course, McDuda. But at this point, I don't have time because I have to go to work very soon. Oh yeah. So I'm going to jump back to quantum mechanics, which has an assumed knowledge of calculus and algebra. So I'm sorry to a lot of you who may not have that assumed knowledge, but I've got to get this done. I also have a lecture. Thank you very much. Notifa. Dynamic. Hey, hey, Mubarak. Ahlan wa sahlan. So, emergency ambulance. I love that. It's called emergency ambulance. Are there ambulances that are not an emergency? What is that about? That is weird. And it's a diesel. Let's just see who's in the ambulance. Oh, they always cover it up. Damn it. Can't see who's in it. Oh, they're slowing down. No, he's gone. We're still so... No Tifa, no Tifa, no Tifa. Alright, this has been Gabversity, where facts don't give a damn about your feelings. Does it bother you if I tend... No, not at all. I just feel guilty. I just feel guilty that I can't explain the calculus. I just don't have time. Because I've got to go through the quantum mechanics. But I do have a lecture coming up on climate change. You're going to love that one. I have a lecture coming up on climate change. That one's going to be crazy. I can't wait to see everyone's reactions. Trigger! Everyone's going to get triggered on both sides. Everyone's going to get triggered, man. It's going to be good. All right. Gabversity, where facts don't give a damn about your feelings. My feelings don't give a damn about others' feelings. It'll be fun. All right. We'll talk to you soon.